Hi everyone, today we are going to look at PDE. So PDE here stands for partial differential equations. Okay, this is different than ordinary differential equation. Okay, so in today's lesson, what are we going to look at will be some topics involving partial differential equation. So we're going to cover linear and non-linear PDE, how to identify linear or non-linear PDE, and how to the order of the PDE. Okay, and then what else? We're gonna look at homogeneous or non-homogeneous, and then what else? So we can also look at types of PDE. And then this is the main part. So upon looking at all these things, we're going to look at types of PDE. Okay, so what is PDE? What is PDE? So a differential equation, okay, a differential equation contains derivative with respect to more than one independent variable. Okay, so we call it partial differential equation. Okay, I'm gonna write it here. A differential equation, your DE, a differential equation that contain derivative with respect to more than one. More, that's the key word here. More than one independent variable. Okay, such as x and t. Okay, anything, x, t, whatever, but if more than one, we have a PDE. Okay, the partial derivative are defined as, so the partial, this is a partial symbol, partial over partial x. Okay, the symbol here is called the partial symbol. Okay, and you can also have partial over partial y. Okay, so we are differentiating with respect to one of the variable that given here. Okay, another notation that you will happen to see is something like this: partial f over partial x, where you have for the variable x and y, it's given as fx xy. Or if you have partial f over partial y, for x and y variable, you can write it as f of y xy. Okay, where this term here, okay, partial f over partial x, you can write f of my small x here. Similarly, if you are using u, I can have partial u over partial x, I can write as ux, and partial u over partial y, I can write as uy. Okay, and if you have a t, so similarly if I have partial u over partial t, I can write it as ut. So these are the notation that you are gonna refer to. Okay, so PDE is very important because many subject areas in engineering and physical science involve solving derivative with more than one independent variable. So example of this equation arises in aerodynamic, electricity, electrodynamic, fluid dynamic, and you can just even like optics. Okay, there are many. You can just Google it. Okay, you can just Google it. Okay, so if I want to look at the classification of PDE, I'm just giving you theory in this course. So to classify the PDE, classification of the PDEs. Okay, how to classify, oh, I don't have my E here, PDEs. Okay, how to classify my PDE. So to classify the PDE, you need to determine the order, the whether it's linear or non-linear. Okay, so we're gonna look at the order first. Okay, so if I have an equation ut equals to uxx, where I can also write it as partial u over partial t equals to partial squared u over partial x squared, another way of writing. So refer to my independent variable with the highest derivative here. So this is my second. So this is second order. Second order. Okay, if I have partial u equals to partial u over partial u equals to partial x, where I can write it as partial u over partial t equals to partial u over partial x, ut equals to ux. So this is first derivative. So first order. Okay, my x and t both are first order, first derivative. Now if I have ut equals to uxxx, okay, now another way to write this, partial u over partial t equals to u partial cube u over partial x cube. Okay, so this is third order. Okay, that's how you determine whether the order for the PDE. Now, when it comes to linear and non-linear, so to check whether the types is linear or non-linear, so let's look at the linear first. To have this linear PDE. So what does things tells you about linear PDE? So we can introduce an operator. So to define this linearity, we use an L operator. Okay, for instance, if I have partial u over partial t minus partial squared u over partial x squared equals to sine x. Okay, so I can introduce a linear operator such that Lu equals to f. Okay, where this f is where my f x equals to sine x. Okay, so I can write this, my L operator here is given as partial over partial t minus partial squared over partial x squared. Okay, so these are my linear operator L. So okay, so where this is my L operator. So if you look at this above here, if I can write it, it acts on a function and produce another function. So it's an operator here. So operators that act by taking the derivative of a function are called differential operator. Okay, now to say it linear, my operator here given by this L alpha u plus beta v, I can written as alpha Lu plus beta Lv. Okay, these are my linear term to check the linearity. So a differential operator L is linear if it satisfies this condition here. For all function u and v and for all constant a and b. So this a and b are constants. U and v are the function. Okay, so I can show you one example. Okay, example here. Okay, show that my linear operator such as partial over partial t plus x partial squared over partial x squared is linear. Show that this is linear. So to begin with, I will start with let me just write it here. So I need to start with my right equation. Right equation equals with my left equation. So I have my right equation such as the operator L, alpha u plus beta v equals to, now I'm going to work it out for this given equation here until I get to my left equation. So what do I have? Partial over partial t plus x partial squared over partial x squared. That's my L. That's my L. And then I have alpha u plus beta v. Okay, so this is exactly what I have in my right, sorry, I've written it wrongly. Okay, on my screen, this is my left and right. So I got it confused here because I should look at my screen, not on. Okay, so let's just change it away. So this is my left hand side equation equals to my right hand side. Okay, so the left now is operator L alpha u plus beta v. I must show it equals to my right hand side. So I can say that this is my L operator and these are my alpha u plus beta v. Exactly like in my left hand side of the equation. Now the next term I need to do is I need to simplify this given equation here. So alpha u multiply with this term here. I have partial over partial t, alpha u, and then this term here plus beta, partial over partial tv. So alpha is a constant, okay, so I can take it on the other side later on, and then plus my x width here. So I have alpha x partial squared over partial x squared u plus, now this term here, beta x partial squared over partial x squared v. So I'm going to write it properly now. So I have alpha partial over partial tu, collect all the alpha term, plus alpha x partial squared u over partial x squared. So this term and this term, written it, and then plus beta partial over partial tv plus beta x partial squared over partial x squared v. Now collecting the common factor or factorizing, I'm taking out the alpha here. I have partial u over partial t plus x partial squared u over partial x squared plus beta partial v over partial t plus x partial squared v over partial x squared. Now look at this term here. I can write it as alpha, my operator L. Okay, so my operator L acting on u plus beta, my operator L acting on v. This is exactly what we have written on our right hand side of the equation, what you should get. Okay, so you start with the left hand side of the equation and you have shown you can obtain the right hand side equation. So therefore the equation given is linear. Okay, so maybe I can show you one more equation, one more example for that. Okay, the second example here that I want to show whether this given equation is linear or non-linear. Okay, so I have this equation utt minus e negative t uxx equals to sine t. Okay, is this equation linear or non-linear? Now you can see that the solution here is in this form of LU equals to P. LU equals to F, where my F is my sine T. In other words, you have a non-homogeneous PDE. Non-homogeneous PDE, but you can still prove this. Okay, so you work on your left hand side first. So the left hand side I want to show as operator L, alpha U plus beta V equals to F, right? So start with here, where I can have for this term here, I can write it as, let me just use my purple pen. Okay, so what I can have alpha U plus beta V partial squared over partial T squared, this is for this term here, minus, okay, exponent negative T does not involve my operator U, so you don't have to worry about this. And then I have alpha U plus beta V for this term here, partial over partial x squared equals to sine T. Okay, this example is different than the earlier one that I've shown. Okay, now let's move on to multiply. So I have alpha partial squared U over partial T squared plus beta partial squared V over partial T squared minus exponent negative T, just leave it as it is. Now this multiply with this, I have alpha partial U over partial x squared, and then plus beta partial V over partial x squared equals to sine T. Okay, now taking the common factor alpha, so what we have here, alpha factoring partial squared U over partial T squared minus this term here, minus E negative T, exponent negative T, alpha is already factored out, so I have partial U over partial x squared. Okay, and then similarly the term this and this, so I have plus beta, factoring beta, I have partial squared V over partial T squared. Now negative Pde will be negative exponent negative T partial V over partial x squared equals to sine T. Sine T. Okay. So I can see here this operator. This looks like, okay, this is my operator L on U. So alpha operator LU plus beta operator LV equals to sine T. Okay, now this is similar with what we have done. So what we've done here, so alpha LU plus beta V equals to my F. So my F here, this is equals to operator L alpha U plus beta V. Now I can show this both sides, so my PDE is linear. Okay, another example. Now let's look at example when the function, the PDE becomes non-linear. Okay, so the third example is show that the operator L defined by LU equals to U partial T is non-linear. Okay, so how can we show that? So obviously there is this operator is nonlinear, but to show that we'll start with this side. Okay, so we have operator L, alpha U equals to, do you want to show it equals to alpha LU for it to be linear? Okay, now you don't have to worry about V because I just have one term involving T here. Okay, so I don't have to worry about the other term here. So this is equals to, my U operator is acting on alpha U. So I have alpha U partial over partial T alpha U. Okay, and then what happened here, my alpha is a constant. My alpha is a constant, but not the U. So I have alpha squared U partial U over partial T. Now this is not equals to alpha L operator acting on U. Okay, this is not the same. So we have a non-linear PDE. Okay, so this is an example of non-linear. Let me see if I can find another example non-linear PDE. Okay, another example of non-linear term. So I'm going to show you this one, this term here. So UX plus UT equals to 0. Okay, so to show this, so I'll start with my L operator on my left hand side. I need to show alpha LU plus beta V. But my U term here, so my U term here is involving my alpha U. So I have alpha U and then alpha U plus beta V for partial squared over partial x squared for this term, and then plus alpha U plus beta V partial over partial T. Okay, so now when you expand this term, alpha U, now I have this with this, I have alpha partial squared U over partial x squared plus beta partial squared V over partial x squared, and then plus with alpha partial U over partial T plus beta partial V over partial T. Okay, there is no way I can write this term operator as so there's no way I can collect the common term. Even if I do, I will end up with this. So if I'm taking the operator L, I will have partial squared U over partial x squared plus partial U over partial T. So this with this, and then plus beta, I will have partial squared V over partial x squared plus partial V over partial T. Okay, so this will never give me, so this is not equals to alpha LU plus beta L operator acting on V. Okay, because I have this term here. So this is not equal. So we have another non-linear PDE. Now to summarize this, what I can say about this non-linear PDE. Okay, so I can say something like this. Okay, so a linear PDE if the unknown function and its derivatives, in this case the unknown function that I'm mentioned here is your U function, your U, okay, appear to the power of 1. of 1. Okay, and then it becomes nonlinear if the unknown function has nonlinear operators, or in other words, it has function, nonlinear function. It has how can I say? It has nonlinear term here. Okay, so example that I can give, I can have several examples here. Maybe you'll understand through this example. So let's look at some of the examples. Okay, so if you look at this equation here, number 1, ut equals to duxx plus fx. Now my unknown operator here, which is my u, is degree 1. It didn't appear anywhere, and there is no unknown function. The function is x, not with u. So this is linear PDE. Now the second PDE, we have utt minus c squared uxx equals to 0. This is also linear PDE because I don't have the operator, the function u appears anywhere. Now 3 here, partial u over partial x plus partial u over partial y equals to 0. Now this is also linear equation. I hope I can give you example of nonlinear. Now let's look at the nonlinear equation here. Partial squared u over partial x squared plus ey sine y partial u over partial x partial y equals to u. Now in this example here, this is linear or nonlinear. My operator u does not appear anywhere. Okay, does not appear anywhere. So that's okay. So this is also linear PDE. Now another one, but this is okay. Now look at here. Ut plus uxx plus uxxx equals to 1. Now this is nonlinear because of this u term here. Okay. Now another nonlinear equation that I can show you is this equation here. xux plus yuy plus u squared equals to 0. Now this is nonlinear because of my u squared. Okay. Now another nonlinear equation I can say is uxx plus uyy equals to sine u. My unknown function, which is my u here. The unknown function sine u. So this becomes the term nonlinear. Okay, so I hope you get difference between what is linear and nonlinear PDE. Okay, so there is another thing that you consider. For instance, this operator here, this is order 2, order 2, order 1, order 2, order 2. No, sorry, this is order 3. Okay, this is order 1 and this is order 2. And you can also classify as homogeneous and non-homogeneous. So I'll tell you the summary for what we want to learn today. Okay, the other part that you would like to know is the homogeneous and non-homogeneous PDE. Okay, this is very important when you want to classify the PDE. Okay, so what is is similar to the ODE, ordinary differential equation part on how you determine the homogeneous and non-homogeneous. So a linear, okay, consider, we're not talking about non-linear now, consider a linear equation in the form, so this equation here refer to my PDE, okay? So we have AUXX plus BUXY plus CUYY plus DUX plus EUY plus FU equals to G. Okay, if you look at my writing here, my U, it looks like a big U. It's actually my small u. So I don't want you to get confused. So I'm going to make it small. Okay, this is all my small u. Okay, so what it tells here, right? This G here. So this A, B, C, D, E, and F and F here, they are the constant. Now G, constant of a given function of x. Constant of given function of x and y. Okay, and I missed out my G here, so it should be my E, F, and G. Okay, all these are the constant. Okay, they are constant of a given function of x. So, and then so we have looked into the standard form, the linear, but this equation here, let's call equation 1.1. Okay, this equation 1.1 is my standard form. And now what it says is homogeneous if this G term here, G equals to 0 for all x and y, and if G, x, y, so G can be a constant or a function in x and y. If it's not equals to 0, then we have non-homogeneous. Okay, non-homogeneous term. Okay, so this is how you classify your PDE. Not just order, not just the linear and non-linear, but just also whether it's homogeneous or non-homogeneous. Okay, now keep looking at this standard equation here. Now we can determine the types of PDE. Types of PDE. So there are a few types. We have parabolic. So parabolic if b squared minus 4ac equals to 0. And then we have hyperbolic if b squared minus 4ac greater than 0. And then we have elliptic if b squared minus 4ac less than 0. Okay, so example of this parabolic equation are the heat diffusion. Okay, so I can put it, this is my heat diffusion equation. Now example of my hyperbolic are the wave equation. Okay, anything involving wave or vibrating of a string. Okay, now elliptic equation, you can have the Laplace equation, and you can even read more about this Poisson equation. Okay, and then we can also have the Helmholtz. Not sure I'm pronouncing it correctly, but these are the example of these types of equation. Now, how do you determine this type? Based on this standard equation just now. Okay, so look at this B this BAC, refer to this standard form. So you need to arrange your given PDE in this form, and then you can determine. So let me give you one example here. Okay, example. If I have an equation given as 17uyy plus 3ux plus u equals to 0. Now, by comparison to my standard form, okay, I don't have a because a is uxx. Okay, and I don't have b too. My equations start with c, d, and f. Okay, so what I have here, I have c equals to 17, and then I have d equals to 3. Okay, f doesn't, we don't need to know the rest, okay, because to determine whether it's what types this PDE is, all you need to use this equation, b squared minus 4ac. Now obviously in this case b is 0 minus, so 4, a is also 0, and c is 17. So it doesn't matter because 0 minus whatever 0, so you get 0 in this case. Okay, so 17uyy plus 3ux plus u. What type did you get? Okay, so we have a type which is called the parabolic type. Okay, because like I said, the method is parabolic if this one, b squared minus 4ac equals to 0. Okay, now the next example, let's look at one more example to determine the type. So I have 4uxy plus 2uxx plus uyy equals to 0. So by comparison with the standard form, I have my a equals to 2 uxx. So look at this equation here. Where is it? See? A uxx. So a equals to 2, and then b uxy. What is my b for uxy? The b is 4. b equals to 4, and c equals to 1. uyy is for my c. Now let's do this. b squared minus 4ac. So I have 4 squared minus 4ac. So 16 minus 8. What do I get? Is 8. Yep, which is greater than 0. Okay, so you have hyperbolic type. So in a way, if you have an equation which is greater than 0, minus greater than 0, you have a wave equation. Okay, now we can also look at another example. Let's look at another example given here. So let's look at this example. uyy minus uxx minus 2uxy. Okay, this is equals to 0. Okay, so in this equation, a equals to -1, b equals to -2, and c equals to 1. uyy is 1. So let's do this. b squared minus 4ac, which is -2 squared minus 4, -1, 1. So I have 4 multiply negative will be positive. So this is also greater than 0. We have hyperbolic. Okay, so this is how you classify. Okay, so the next part is, these are all the introduction to PDE, where you have known the classification and then you have known the types of the second order PDE. Now another question that I can show you is whether another example. Let's look at another example. Okay, example is determine if the given uxt equals to exponent negative 9t cos 3x is solution to the PDE given as partial u over partial t equals to partial squared u over partial x squared. Okay, so that's the question. Now this can also be a common question in PDE. So how to determine whether your given u function here, this u function here, is the solution to this given PDE, where I can also write it as ut equals to uxx. Okay, so this question is not that hard. So given, so I would like to write as given uxt equals to exponent negative 9t cos 3x. So you differentiate respect to t. So I have negative 9 exponent negative 9t cos 3x. That's all I can do. And then this u differentiate with respect to x. So differentiate exponent negative 9t will be a constant here because I'm differentiating with respect to x. So cos will become negative sign. So I have negative sine 3x, and don't forget my 3x here will give me 3. So that will give me to negative 3e negative 9t sine 3x. Okay, and then the equation is given as ut equals to uxx. So I have to differentiate second time this equation here. So differentiating second time, so 3 and 3 will give me minus 9 e negative 9t. Differentiate sine will give me cos 3x. Okay, so look at this equation. So it says show that whether the function satisfy this, and we can see that my ut I have obtained as negative 9 exponent negative 9t cos 3x, which is also equals to my uxx. So they are we got the same equations. It satisfied my given ut equals to uxx function. So therefore we can say that, so I don't know why it went down, so maybe I can just put it like this, equals to uxx. Okay, ut equals to uxx. So we can say that this equation, this given uxt, which is exponent negative 9t cos 3x, is the solution to the PDE ut equals to uxx. Okay, so this is the introduction to partial differential equation that covers classification of PDE, such as you have order, linear, non-linear, homogeneous or non-homogeneous, and then you also I've also introduced you to the types of PDE. You have hyperbolic, parabolic, and elliptic, and then how to find the solution for the given equation. Okay, so I guess that's all for today. Thank you.